Okay, today we're going to be looking at how to work out the nature of stationary points using the sign test. And if you don't know what a sign test is or what the stationary points are, I do have another video where you can look at what stationary points are. But here's how you can use the sign test to work out the nature of stationary points. So first thing we do is let's first work out the stationary points to this equation here, y equals 9x squared minus x cubed. First thing we do is differentiate. To differentiate this, we can use the power rule. So we get 18x minus 3x squared. Now to find the stationary points, we let the derivative equal to 0 and we solve for the values of x. So in this case, if we wanted to solve for this equation, we can factorize out a 3x and we'll be left with a 6 minus an x. Now to solve this equation equal to 0, we can say either x can be equal to 0 or that 6 minus x can equal to 0, in which case x is simply equal to 6. So now we have two values for our stationary points, but how do we know what kind of stationary point it is? How do we know whether it's one of the three stationary points? So the three stationary points you can have look like the following. We can have either a minimum, or we can have a maximum, like this, or we can have a horizontal point of inflection, and that would look like this. Okay, it's just a rough sketch, nothing too fancy. But we can have three types of stationary points like this. And what exactly are your stationary points here? Well, there would be this point, and this point here. They are stationary because if I draw a tangent line at these points here, you can clearly see that the gradient of the tangent lines at each of these 3 points are 0. So our goal here is to work out which one of the three on my screen here do we have at x equals 0 and at x equals 6. And for that, we're going to simply be using the sign test. So I'm going to scroll up a bit and I'm going to draw a table to dictate what the sign test is. The sign test has 3 rows. You have your x values, you have your derivative values, and you also have the sign. Okay, and let us suppose we first try to work out at x equals to 0, what type of stationary point do I have? So to work this out, I'm simply just going to have 3 columns, and in the middle column, I'm going to have x equals 0. Now, what I do here is I choose a value for x that is both slightly less than 0 and slightly more than 0. And two numbers I can think of that are slightly less and slightly more than 0 are -1 and 1. So now let's fill in the table. If I wanted to work out what is the derivative when x equals to 0, I would simply say the derivative is 0, because x equals to 0 was a stationary point. We just solved that it was a stationary point. Now, how would I work out the derivative when x equals -1? Well, when x equals -1, I can simply plug it into this derivative equation here for -1. So this would make it -18 minus 3. That would give me -21. So my derivative at x equals -1 is -21. This number tells me that the gradient of the tangent line when x equals -1 is -21. Now what about when x equals to 1? Well, when x equals to 1, let's sub it into this equation here. We get 18 times 1, which is 18, minus 3 times 1 squared, which is -3. That gives us 15. So this tells us that the gradient of the tangent line when x equals to 1 is going to be 15. So the tangent line will look like this. So now we have these two tables filled in, these two rows filled in. Let's now work out the last row. The sign is pretty much asking us whether our tangent line is rising upwards like this, is it flat like this, or is it falling like this? If your derivative at x equals -1 is a negative number, -21, that would mean the gradient of the tangent line is negative. And the gradient of a line, if it's negative like this, clearly means it's falling. So in this little box here, I'm just going to do a line like this to show that my gradient is falling, or at that point, the gradient of the tangent line is negative. When the gradient of the tangent line equals 0, you can say that it's simply going to be flat like this, because if you have a look at these 3 diagrams here, the tangent line, at each of these points here, the tangent line has a 0 gradient. Hence it's not increasing, nor is it decreasing. It's just completely flat like this. So over here, I'm just going to say it's flat like this at x equals 0. And then when x equals to 1, my gradient is more than 0. My gradient is positive, so that means my tangent line will be rising like this. So that means I can write it like this. So now we can look at our sign test, and we can ask ourselves, which one of these three images does our sign represent the most? Well, what I can see is the graph, it's going x increasing order from left to right. So as x increases from -1 to 0, we can see it falls like this. But then when x equals 0, it's flat. And then when it's more than 0, it increases like this. Okay, so that means this stationary point here demonstrates that it's actually a local minimum. Okay, so we can clearly say, just from the sign test here, just from this little picture, we can say it looks something like this image here. So I can write a conclusion statement that says, at x equals 0, okay, the graph is a local minimum. It is a local minimum. So now I want you to pause the video, and I would like you to try the same sign test for the second stationary point. I would like you to try it for when x equals to 6. Pause the video and give it a go. Okay, now let's try it ourselves. We're going to make the middle row here, we're going to make that value equal to 6. And the reason we're making it equal to 6 is because we're trying to compare the points to the left of it and to the right of it. We know that the derivative at this point here is going to be 0, so let's just fill that in there. And that means our sign is going to be completely flat at this point here. Now let's pick x values that are slightly less than 6 and slightly more than 6. So values that are slightly less and more than 6 I can think of are just 5 and 7. Make it easy, don't make it too hard for yourself. Now that we have this, what we can do is substitute in 5 into our derivative value, into our derivative expression, and get the value for the derivative. So 5 times 18, that's 90, minus 3 times 5 squared, that's 3 times 25. So that would be 90 minus 75, which is simply just 15. So our gradient is 15 at this value. Then at x equals to 7, okay, let's also do the same thing here. When x equals to 7, the value of this here is just 18 times 7. And 18 times 7 is simply just 126. And then we can do minus 3 times 49. And 3 times 49 is the same as 3 times 50, but then you just have to minus away a 3. So that would be 147. So 126 minus 147, that would give us minus 21. So now we can have our derivatives like this and like this, and we just need to draw a sign. Does it look like it's falling, or does it look like it's rising at x equals 5 and x equals 7? Well, at x equals 5, the derivative is 15. That means if I were to have a sketch of my graph and I drew the tangent line at the point x equals 5, the gradient of the tangent line would simply be 15. So that means it would be rising like this at x equals 5. But then when x equals to 7, you can say that it's simply, you can say that it's falling at x equals 7 because the gradient of the tangent line at x equals 7 is negative 21. It's going to be falling like this. So hence we can say it's falling like such. And just from this little sketch here, this sign sketch, we can see it's rising, then it's flat, then it's falling. Okay, and that clearly shows that this point here is going to be a local maximum. Okay, so now that we've identified that, let's have our little statement at the bottom. We can say that at x equals 6, right, the value of the stationary point is a local maximum. Okay, and that's how for this question we identified both the stationary points as well as the nature of the stationary points using the sign test. Okay, this is our next question here. Y equals x cubed, take x squared, take 9x. Pause the video and try to find both the stationary points as well as the nature of the stationary points for this equation here. Okay, let's first work out the stationary points. Okay, so the derivative dy over dx, okay, we can simply use the power rule. That'll get us 3x squared minus 6x minus 9. And now to solve this, we can let the derivative equal to 0. Okay, so now what we can do is we can just divide both sides by 3. So 0 equals to x squared, take away 2x minus 3. And we can simply factorize this as x minus 3, x plus 1. That means our two stationary points occur when x equals to minus 1 and x equals to 3. And we did that using the null factor law. So now that we have, these are our two x values, how do we know what the actual nature of these stationary points are? So again, it can either be a maximum like this, a minimum like this, or it can be a horizontal point of inflection like this. So let's first use the sign test and work out what type of stationary points these two are. So I'm going to draw my 3 rows, the x value, the dy over dx value, as well as the sign. Okay, so these are my 3 rows, and then my 3 columns will be my 3 x values. And the 3 x values will be chosen based on the fact of where I have my stationary point. So 3 rows, 3 columns. Okay, now that we have our table, let's now do it. So we know, we'll start with x equals negative 1. Okay, we know that negative 1 will be in the middle because that's our stationary point. And we're going to choose x values slightly to the left and slightly to the right of negative 1. So that's going to be, in this case, negative 2 and 0. And we know the derivative when x equals negative 1 is going to be 0 because this was our stationary point. Let us now work out the value for the derivative when x equals negative 2. So I sub in negative 2 into this equation here. So when I do that, I get 3 times negative 2 squared minus 6 times negative 2 minus 9. This will give me 12 plus 12 minus 9, and that's just 15. So the value for the derivative when x equals negative 2 is going to be 15. Now let's do the same thing for 0. If I sub in 0 into this equation here, these first two terms will simply cancel, and we're just left with a minus 9. So now just by looking at our derivatives, we can say when x equals negative 2, the gradient of the tangent line, it will be 15, which means the tangent line will be rising like this. So I'm just going to do a little line upwards like this. When x equals to negative 1, the derivative is 0. It's a stationary point, so it's going to be flat like this. And then when x equals to 0, we can see the derivative is minus 9, which means the gradient of the tangent line at the point x equals 0 will be negative, so the graph is falling like this. So it's falling like this. And just by using our sine table, we can have a look that it's going to be concave down like this. It's going to be a maximum point when x equals negative 1. So I can write a little statement that says at x equals negative 1, okay, the value or the nature of the stationary point is going to be a local maximum. And that's how you do it for x equals negative 1. Now we just have to do it for x equals 3. So I'm going to rub out all the values on my sine table. Okay, and now we're going to do the same thing for x equals 3. So 3 goes in the middle. We're going to choose x values slightly to the left and slightly to the right. So a 2 and a 4. So now that we have this, we can say that the derivative is going to be 0 when x equals 3. We can say that to work out the derivative when x equals 2, we can just substitute it into this equation here. So 3 times 2 squared minus 6 times 2 minus 9. That'll give us 12 minus 12 minus 9. So that these two will cancel out, we get minus 9 here. And then when x equals to 4, we can do the same thing. Sub it into this equation. 3 times 4 whole squared minus 6 times 4 minus 9. 4 squared is 16, times by 3 is 48. Minus away 24, minus away 9. So this will give us 24 minus 9, which will give us a 15. So that is our derivative, 15. And we can do the same thing just by looking at it. When x equals to 2, the gradient or the derivative at that point is minus 9. So that means the gradient of the tangent line is negative and falling like this. And then when x equals to 0, it's a stationary point, so it's just a flat line. And then when x equals to 4, the gradient or the derivative is 15. That means the gradient of the tangent line is rising like this. So we can say it's rising. And just by following the path of the sine, we can see it's concave up like this In other words, this point here is going to be a local minimum. Okay, so now we can write our little statement. At x equals to 3, right? The value of our derivative is a local minimum. Okay, and that's how we do it for this cubic here. Okay, and this is our last question for this video. I'd like you to pause and try it now. Okay, so let's work out the nature of the stationary points by first working out the stationary points. So when when we differentiate this, we get dy on dx is going to be equal to 12x cubed plus 48x squared plus 48x. And we differentiated this using the power rule. So now that we have this as our derivative, let us now make the derivative equal to 0 and solve for this equation here. Okay, so now that we have this, what we can do is we can simply divide everything by 4. So we get 0 is equal to x cubed plus 4x squared plus 4. And now, 4x. And now what we can do is we can factorize out an x here. So we have x and then x squared plus 4x plus 4. And we can recognize this is actually a perfect square. So we can say that 0 is equal to x times x plus 2 whole squared. Okay, we can factorize this as x plus 2 whole squared. So now to solve this equation, we can say that x must either be equal to 0 or x plus 2 must be equal to 0. And if x plus 2 equals to 0, that means that x is equal to minus 2. So these are your two stationary points. Let us now work out the nature using the sign test. Okay, so we have, this is our stationary point. So we draw our table again. Okay, so we have x, we have the derivative dy on dx, and then we also have the sign. Okay, and then we have 3 columns. Fantastic. Now let us have our numbers. We'll start with x equals 0. So we have 0 here, and now we choose a number slightly less than 0, slightly more than 0. That'll be minus 1 and 1. Now let's work out the derivative. The derivative when x equals to 0, well, that's simply just going to be 0 because that's a stationary point. And then when x equals to minus 1, okay, we can just sub it back into our derivative expression and work it out from there. So when x equals to negative 1, we can work out that it's going to be minus 12 plus 48 and then minus 48. 48 and minus 48 cancel, so you're just left with minus 12. So it's minus 12 over here. Then when x equals to 1, okay, I'm not even going to work it out. It's going to be too much effort for me to sub it into this equation. But a good note of rule is if x equals to 1, then all of these terms will be positive. So it means a positive plus another positive will simply be equal to a positive number. So I'm just going to write positive over here. Cool. So now let's look at our sign. Okay, when x equals negative 1, the derivative is minus 12. That means it's falling. Okay, the gradient of the tangent line is falling like this. When x equals to 0, it's a stationary point. You get the idea. And then if the derivative is positive when x equals to 1, it doesn't even matter what value it is. You just automatically know it's going to be rising like this. Okay, so that's what we're going to do here. So it's going to be rising as such. So now that we have this, we can say, if we follow the sign, it's going to look something like this. So it means at x equals to 0, at x equals to 0. Can you tell me what type of stationary point it is? It is a local minimum. Okay, so now we have to do the same thing for when x equals to minus 2. It is a, what is it? Let's work it out now. So I'm going to redraw my sign table, this time just replacing each of the values. Okay, so now that I have this, let us now work out the value of the nature of the stationary point. So we make x equal negative 2 inside the middle table. We choose a number slightly less and slightly more than negative 2, so negative 3 and negative 1. Okay, and then now we can work out what is the value of each of these values here. We know the derivative when x equals negative 2 is 0, and we already worked out that when x equals to negative 1, the derivative was simply going to equal to negative 12, I believe it was, but we can check again. So we get negative 12 plus 48 minus 48. Yeah, I was right. It's negative 12. Okay, now let's sub it in when x equals negative 3. I can almost guarantee you that when we sub in negative 3, it's going to be a negative number, but I don't know yet. Let's check. Oh, sorry, it's going to be a positive number, but let's check. So negative 3 cubed. Okay, we sub it into here. We get negative 27 times 12. Then we get plus 48 times 9. Okay, then we get plus 48 times 3, or negative 3. Okay, so we can factorize this component here as just 48 times 6. 48 times 6, and we can rewrite, what can we rewrite here? We can rewrite this here as simply 3 times 3 times 3 times 12. This here is the same, okay, that doesn't really help us. Okay, we can say that 48 times 6, let's work that out here, 48 times 6 using our calculator, is going to equal to 288, and then minus 27 times 12, that's going to equal to minus 324. So I was correct, it would be negative. It doesn't really matter what the value of this is, I just know it's negative. Okay, so when in doubt, don't really care about the value, just put it's negative. So now we have this situation here. We have the derivative is negative, then the derivative is negative here as well. So that means the sign at both these values will be like this. Okay, but then it'll be a 0 over here. So what this means is the graph is decreasing, then it flattens out, then it decreases again. This looks like a horizontal point of inflection. Okay, this looks like a very big horizontal point of inflection. So if that were the case, that's what we can say over here. It is a horizontal point of inflection. And that's how you use the sign test to determine the nature of stationary points.